SpaceX ISRO. SpaceX ISRO. Same. No, actually ours is roughly half the size of theirs, which makes our mission way more complicated and difficult. And to make sure you understand the complexity here, I've created a 3D model of ISRO SpaDex satellite, showing and animating the mechanisms and how they work. I even dug into ISRO's videos and found so many things we missed during the launch. And to end this off, we will talk about the future of the system, what is even the point of this test. Let's get started on why both look so similar. SpaceX uses something called the NASA Docking System or NDS. ISRO uses ISRO Docking System. That's not the official name, but let's call it IDS. Both try to align on something called the IDSS, which is the International Docking System Standard, which is NASA's open standard on how the interface of docking should look like, what should be the size of the petals and the ring, etc. But if you see closely, while they look similar, there are a lot of difference. Like ours has a hole in the petal. Like there's a long slit in the petal. So we take philosophical inspiration with IDSS, but it's fundamentally different. Before we talk about the 4 steps that go into docking, let's quickly talk about what happens even before you start docking. And here there are lots of lasers. See, when the satellites are very far away, like 20 kilometers away, the satellites each have a satellite link called the inter-satellite link, ISL, and they can talk to each other via radio communication. But as you start coming closer, now you require a lot more precision, and here is where ISRO starts up LRF, or the laser range finder. This laser range finder works in a simple way. One satellite will fire a laser, the other satellite will have a retro reflector, which is a reflector which will send a light back in the same direction as it came in. If you might remember, Chandrayaan 3 and 2 had a retro reflector on top of them. ISRO says this system is good for 6 km to 200 km. But as you come closer, now you require more precision. From 2.5 km to 0.4 meter, there are 2 groups of sensors that are triggered. One is the rendezvous sensor. Rendezvous, for those who don't know, means a meeting. So many times a space docking is called a space rendezvous or a space meeting. And the other is the proximity docking sensor, which starts even closer, like 30 meters in. Both of these also use lasers, but instead of bouncing off the light, they have laser targets. So one is firing laser on the other, and there's a receiver on the other satellite, and there's no bouncing off. So it just receives the laser and then you know the distance. Finding these lasers on the satellite has been tough because ISRO hasn't still published a paper on it, and I had to go through a lot of these images. But what I think is, on this CAD image that you see, the one above the docking sensor looks like it has a laser beam and a reflector together, and the one on the other side has to be a regular laser target. I'm not sure, we will see when more details come out. There are sensors on the ring as well to know when the satellites have touched each other. To test all this, ISRO created this super cool robotic arm jig which moves the panels close by or far away, and then they can test the outputs of the either satellite sensors. Very cool stuff. It looks very majestic with that robotic arm doing its own thing. Also remember that these satellites have cameras as well monitoring this whole docking system. There's also a high definition camera. Unfortunately, they haven't shared the whole footage from that camera yet, but with this camera they can monitor live as well as decide to not maybe pull out of the docking and not go ahead with the docking if they see any issue. Now for the actual docking, you have 3 or 4 steps roughly. One is soft capture, other is pull in hard capture, and then comes your fuel, power, communication transfer, etc. The thing that meets first is of course this petal parts, right, which is on the front ring, these petals. These petals are cool, right, because they're tilting inward, so they self-adjust and center to each other. But even after centering, after they meet together, what will you do? How do you hold them? Because they could go loose again, right? It's not magnetic or anything like that. They'll just stick together, but they could go loose. So you need a way to do soft capture, like softly keep them together with a less weight or a smaller mechanism. Now if you see NDS, on the petals you'll see this thing, right? Like there's something on the petal. This is their soft latch that goes and hits a passive striker inside the other side. But on our system you don't see anything like that, because this slit that you see in the petal, that is space for a stick like item or like a small hinge to go across the petal. I hope through my animation you understood what is happening. This was a headache to find because ISRO's official animation does not show this. By the way, if you see a golden animation on screen, that's ISRO's, mine is the white one. There are some segments of ISRO's videos where you can roughly or briefly see this gray like soft latch in between, and there is one segment in ISRO's videos where you can see this latch being activated. It's for like 1 or 2 seconds. It's very quick also, and it's very interesting that we could see that in like a working state, because most of these test videos it looks like this soft latch is disabled, so they are only testing like interfacing, and only in some tests in this video they are actually testing the soft latch. So this is the soft capture part. If you're liking the video so far, do consider subscribing. Now comes the pull in time. If you have noticed, one of the docking ports has popped out. There are reasons to do this on approach. One is, of course, you must have guessed, for some sort of shock absorption if you are coming in too fast. The other is to stabilize at an angle. If you look at the top of Dragon's NDS, it's a multi-axis hexapod system. So it can, it can do like multi-axis rotation and all of that. It can balance itself. This gives you two advantages. One is, of course, better shock absorption. You have more motors and axis absorbing the shock. The other is you can stabilize it at any angle, which means you can come slightly like from the side or from the top. You don't have to come dead straight in, right? Because you can simply change the angle of your front ring and then have a soft capture. The 42 motors on NASA system give you the ability to do that, but ISRO does not have this luxury with at least version 1 of IDS. It's a 2-motor single axis system, meaning you go out and in, that's it, which means we don't have a lot of scope for large shock absorption. And second problem is you have to come dead straight in, right? You can't have a lot of angle in your entry. This creates a problem, which is you have a smaller room for error versus something like the NDS system, and which also means you have to come extremely slow and extremely dead straight. This is why I said our system makes it more complicated to dock than Dragon. There is such a small margin for error. To add to this problem, both of the satellites are very light. They are just 220 kgs roughly each. So when you dock something to ISS, you are docking something relatively lighter to something very heavy, right? ISS is very heavy, but here it's just two light sats coming in close to each other. So you can't come in very fast. You have to come extremely slowly. I think it's like 10 millimeters per second kind of rate. Very slow. I hope you appreciate the engineering that's going on here. Many of you might wonder why not make a bigger one then. We'll talk about it. So these two motors pull in the satellite. Now you have to make it hard lock with each other, right? The internal latches are small. They can't do a lot of load and they could be delicate. In case of NDS, you see these things on the ring. These are hard latches, right? They come out and latch to the other side of the ring. Also, if you notice, there's a red seal because these are used on the space station. They have atmosphere, they are pressurized, so they need a seal. We don't need a seal, at least on this one, because there's no pressure, there's no air. If you see our ring, there are no latches, right? Instead, we have this external latches that go on the outer side of the ring, and they like go in and grab the other side of the ring hole. While this looks simple in my animation, the actual mechanism is like a multi-gear system. It's like one gear on top of the other, and this whole thing is springed as well. So yeah, it's a very complicated system there are 3 of this on each ring. And you can see in the models, in my model, this so beautifully aligned. While modeling, I did not model this separately, right? I just made one ring on the left. I used Blender 3D, by the way, and then I rotated it on the other side, and they're just aligned. This system is called, when you have similar systems on the other side, it is called androgynous system. Next, in ISRO's animation, you see these pins touching each other. That is the power transfer module. So these two things will touch each other and communicate power and communication, etc. NASA has this all on the ring, so fuel, power, etc. are on the ring itself. Let's talk about future and future improvement. Why are we doing this, right? Why is ISRO doing this? This test is important. Closest will be Chandrayaan 4, where there will be 2 separate rocket launches and they have to dock in space and dock around the moon. Next up will be Gaganyaan capsule, where they could do docking with our future space station. And then comes the future human moon mission for 2045, which ISRO is planning. But the problem is, in its current form, it is very limited and there are many things that need to improve. And ISRO has said they will plan SpaDex 2 and SpaDex 3 and more. What are these improvements? If you see the official docking video where they declared that docking is done, there comes a point where you can see ROD, which is relative orbit determination and propagation. And the website mentions that they used a GNSS based, as in GPS, Navig and all of this navigation systems based algorithm to determine each other's position. Now the issue is, on Earth this is great, but the moment we talk about moon, for which Chandrayaan 4 will use this, there is no GPS there is no Navig there. So this is something they have to work on. This head they are working on it. I'm not sure if they will do it on this test. Second is, like, first docking attempt was very manual in nature, lots of intervention. This has to happen with 100% automation, and they had said that they might retry this docking with 100% automation. For Chandrayaan 4, therefore this system is perfectly fine and likely will be used. But for space station and Gaganyaan, we have to make the full bigger 800 mm with a seal IDSS level system, especially since one of Gaganyaan's plan is to dock this with the International Space Station someday as well. Everything has to be based in the ring, right? From your power to your fuel transfer to the seal to your hard latches, everything has to be in the ring, because the more external systems you add, the more mechanical complexity increases and potential for failure. So ISRO has said that eventually that is their plan. Either they make it on their own or they buy it from outside. But yeah, let's see. So yeah, this was it. I hope you enjoyed the video. Do consider financially supporting the channel by becoming a member. And if you become a member, do join the private Discord where we chat and have calls, etc. Thank you. जयम शर्मा, चैतन्य, प्रदीप मोहनदास, विशाल भारत, कृपाल पटेल, शौनक पेरनी, कुमार अखिल, चंद्रबदन सिंह, श्रीकांत कापड़े, मुंद्र, विशेष वत्सल, व्हाट्स न्यू, विद्यासागर रौनकी, वर्शिष्ठ रेड्डी.